morning, students. And our today's menu is the kinetics of the parallel reactions and consecutive reactions or the sequence of reactions. We will say parallel reaction. Parallel reaction. It is also called as parallel, or it is called as competing reactions. Parallel reaction is also called as competing reaction, or it is also called as side reaction. In nuclear chemistry, we are going to see, instead of side, it's a branching decay அப்படின்னு சொல்லுவாங்க. Here we can call it as a branch reaction and also this. And when will you call your reaction as a parallel reaction or competing reaction or a side reaction or a branch reaction? For example, A giving B. If this is the equation, it gives only one product B. It's a direct reaction. Almost all of them consist of the B product only. But in many of the organic reaction, if you see, in addition to the main reaction, we are getting side product. That side product is the same reactant may undergo two different mode of the reaction, A giving B and A giving C. Let it be assumed that rate constant for the forward reaction for the A to B and for the A to C is K2. Not only two products are formed, sometimes three products may be formed or four products and so on. For simplicity, we have written it as a three products, let us assume, B and E. Here we have given how many moles are formed from when 1 mole of A is reacting, 1 mole of B, 1 mole of B, 1 mole of E. Whether in all the reaction it will be the case, no. Let us take some more general form, N1 of B, N2 of D, N3 of E and so on, and let it be a K3. And why we call this a parallel reaction? Sometimes we write this like this, parallelly taking place. We also represent this into this. We call this a parallel reaction. Here, rate constant, depending upon the rate constant, one reaction would be taking place very fast, the other reaction would be taking place slowly. Therefore, we call it as the competing reaction. They compete with each other. And of these three or four or five or two, one product would be obtained in a larger amount, another product in a minor amount. The larger amount product we call it as the main product. Main product. And the lesser amount as minor product. If these three are present, here one more is a less minor product, and so on. You can get it. How to identify which is a major whether B is a major product or D or E? How to identify? All are depending upon the rate constant of B, D, and C. How to find out? The rate constant may be higher or lower, and this one rate constant. Suppose how many are formed from 1 mole of A? That is the distinct factor for N1K, N2K, N3K. Find out these values. Of these values, which is present in all proportion, that is called the main product. Which is present in lower, that is called S, that is S minor product. The intermediate product, that is minor product. If you understand this, first write down the problem Then we will go for further discussion with this parallel reaction. Take down the problem. In a reaction, a parallel reaction, identify the product which is present in larger proportion, which is present in larger proportion, which is the least proportion. How to identify this? For which not only taking the rate constant, but also you should consider what are the stoichiometry of the products. Here, multiply this 2.8 into 10 power minus 3, and this is 5.6 into 10 power minus 3, and this is 9 into 10 power minus 3. Therefore, if you give off this sum of the concentration, total concentration of the products, here its proportion is 9 into 10 power minus 3, its proportion is 5.6, its proportion is 2.8. Therefore, which would be having higher in amount, T would be in higher amount, into T will give you the total concentration. If it's given, multiply this, you will get the actual concentration. But from this N1 into K1, N2 into K2, you can easily tell which is having higher yield, which mode would be having lower yield. Accordingly, you will get B product as higher concentration and C product as the intermediate and B product as the least amount. And this can be given diagrammatically given in the concentration versus time plot. In all the plot for this parallel reaction, the exponential decay is due to the reactant and an exponential increase in the concentration from the zero. These are all due to product. If two products are formed, you will get two curve. If three products, three curve, and so on. For the given problem, I have given a problem A to B, then C, then D, etc. And some K1, K2 are given. Now, this is the more concentration one, is not. This is intermediate concentration. This is the less concentration. Therefore, this is the major product. This is the minor products. This is the intermediate. And tell me the answer. The upper curve is due to which product?
D, sir.
D. Next one.
C.
Next.
B.
C. Next
B.
one.
B.
D. If you understand the concept, you can get the answer very easily. Now we can go to another type of problems, another in the same parallel reaction. What is another type of problems? Here, what is the percentage of the ith mode that is taking place in this one? What is the mode? Here, three different is called this one. This is the first mode. This is the second mode of reaction. This is the third mode of reaction. Therefore, generally we call it as the ith mode. And what is the percentage of the ith mode? That is, A is undergoing decomposition or reaction. If 100% of A, 100% of A undergoing decomposition or reaction, of the 100%, how much percent is allotted for the mode 1, how many percent to the mode 2, how many percent to the mode D. And this percentage of the reaction is constant throughout the kinetics. Or in terms of this, what is a fraction? In terms of fraction means divided it by 100, you will get the fraction. And how to calculate how many percent of this would be going, or how many fractions we go through the first mode of reaction and second mode and third mode, for which you are in need of you are made of, what is the overall K values? Overall K value. How to find out the overall K value? That is the net K value for undergoing decomposition to B, C, and D. That overall is summation of KIs. Summation of KIs. What do you mean by summation of Ki? What is the value for the first mode of reaction? What is the rate constant for the second mode? What is the rate constant for the third mode? Some of these. With this rate, it is going to undergoing reaction. A is undergoing reaction. Therefore, we call it as K overall. And of this overall, what is the fraction of K1? What is the fraction of K2? What is the fraction of K3? We calculate it using Fi, that is fraction of ith mode is given by Ki, the K value for that ith mode by K overall. Instead of writing overall, we will write it as a KT, K total. K overall can be written as a KT. Therefore, in this way, you can find out what is the percentage of A undergoing reaction to give B. What is the percentage? If you want percentage, multiply. This is the fraction you will get. You multiply it with 100, then you will get the percentage of B going to give C. Wow, how much percent of A would undergo reaction through the K3 mode or third mode of reaction, and so on can be calculated very easily. If you now understand this, now work out this problem. In a parallel reaction, is given as 1.2 into 10 power minus 3 A, sorry, B, 2.4 into 10 power minus 3, and 0.4 into 10 power minus 3 C D. What is the overall rate constant? What is the percentage of B mode? B mode, what is the percentage of B mode? That is, B mode means the mode in which the product B is taking place. First, to find out the KT total, or sum of these, all these ones. Summing up, you will get 4 into 10 power minus 3. 4 into 10 power minus 3. Do you follow this? Hello?
Yes, sir.
Do you follow this? And what is the percentage of P mode? That is fraction. You can calculate the fraction Fi as the B mode Ki by Kt. What is the mode B mode? The K value is equal to 1.2 into 10 power minus 3 divided by Kt, that is equal to 4 into 10 power minus 3. Personally, you will get it as this and 0.3. I think so. Is not. Answer is 0.3.
It's a point, sir.
Okay, this is the fraction of the mode through which A undergoing reaction to give B 0.3 per, not percentage. It is a fraction. You are asked to calculate percentage, multiply the fraction by 100, you will get 30% of the A undergoing decomposition to give B. Similarly, now work out for the percentage of C and percentage of D. Similarly, work out what is the percentage of A to C mode, what is the percentage of A to D mode. Tell
C
me,
60% and
C
D
60% and D would
D
be
10.
10%. If you are right, the total should be equal to 100. Therefore, in this way, you can calculate what is the percentage of the particular mode that is taking place or fraction that can be calculated. If you know this one, you can calculate another this half-life of this reaction. It's the first order kinetics. What is the T half overall? What is the T half of ith mode? It is possible for you to calculate individually. How to calculate the individual one that is given by T half is equal to what is the formula generally you are using? That is equal to 0.693 by the K values. This is a equation used for first order kinetics. Are you sure? First order kinetics 0.693 by K. Here K for overall reaction, you should put
K
KT.
total.
And for T half of I, what is the general equation? 0.693 by
KI.
by Ki. Then what is the relationship between, anybody tell me the relationship between T half overall? What is the relationship between T half I with T half? What is the relationship? Immediately divide one by another, you will get the relationship. That is T half overall by T half for the ith mode would be equal to Ki by Kt. Okay? Or T half of I is equal to T half of I is equal to T half into Ki by Kt. This is the relationship. What is this? Ki by Kt. What is this? கொஞ்ச நேரத்துக்கு முன்னாடி தான் போட்டீங்க.
SI.
And a fraction of that ith mode. Therefore, the overall T half, multiply it with a fraction of the ith mode, you will get this one. Therefore, this equation can be applied when T half and fraction is given. Overall T half and fraction is given. You can work out this. If this can be obtained, if individual KIs are given, you can work out using this equation itself. Therefore, what is the problems given? Whether individual is given, you can calculate individually. Instead, individual is given, overall T half is given, and fraction of the mode is given. Go by this equation. Therefore, either of these can be used and take down that problem for the first order, parallel reactions of the type A giving to B 1.1 into 10 power minus 2 per second, giving C 1.8 into 10 power minus 2, giving 3D 2 into 10 power minus 2. Here the stoichiometry is not necessary for the calculation of T half. Understand this. The stoichiometry is necessary to calculate what is the concentration of B, what is the concentration of C, what is the concentration of D. Then only it would be necessary. The stoichiometry is necessary. Otherwise, use this one. And here it is given. Find out the overall T half and the T half of I. whether you should go by the equation T half is equal to 0.693 by K, whether we can make use of that equation, or you should go by the equation T half of I is equal to fraction of the I and T half. Here, what is the problem given? Here, K1, K2, and K3 are already given. Individual Ks are given. Therefore, you can apply directly the individual T of is equal to 0.693 by T. You can apply this. For overall T, you have to sum of this, you will get the overall one, and then go for this. Okay? Or you put it as 1.2. For summation, it will be very helpful to you. Okay? Take down the next problem. A giving B and C and D. B mode, 80% of the mode. C, 10% or 15%. And D, rest D. If T half of the overall T half is 2 hours, overall T half is 2 hours. What is the T half through the mode B, through the mode C, through the mode D? Is it possible to calculate or not? It is very easy, you can calculate. The T half of the overall is equal to given T 2 hours. Here, fraction of the mode of the reactions are given. K values are not given. Therefore, you should go for the equation T half overall or T half of any mode is equal to the fraction of that I mode by T half overall. And T half of I instead of I put B mode. What is the fraction? It is given as 80%, but here you are made of fraction. Therefore, 0.8 into 2. T half of C, it is 15%, is equal to 0.15 into 2. And T half of D is equal to the rest is 0.05 into 2. And multiply this, you will get the half-life period. Okay? This is the way you can calculate the half-life. And the next one is at concentration of various species. At the time T. Here A is giving B or C or D, whatever may be, it's a parallel reaction, giving this one. At time equal to 0, the concentration of A 0, B is equal to 0, this is 0, this is 0. At time T, the amount of A is left as AT, then B as BT, C as CT, what is the D as DT? What is the concentration of A? And what is the concentrations of the products? What are the concentration of the products? For which I am going to give a simple equation, not simple. It is an equation, general equation. You can make use of that equation and find out the concentration. Take down the equation for AT. AT is equal to, as usual, our risk argument. AT is equal to A0 e power KT, or we have given as the KT in the irreversible reaction. And here KT for the reversible reaction, for the parallel reaction, K is equal to given by K1 plus K2 plus K3, the overall reaction, and so on. T. Therefore, here it is the fraction unreacted. This is called fraction unreacted. Multiply this, the amount left is of time. Then what is the concentration of any term at time t? Here it is not the C concentration. Don't think it's the concentration of the ith mole. At that time, T is given by, that is given by Ni. What is Ni? Number of moles formed. இங்க கொடுத்திருப்போமே 2, 3, 4 அப்படின்னு போட்டோம்னா, here it is very necessary. Ni into Ki, the rate constant for that particular mole, divided by the total rate constant K1, K2, K3. You have already calculated KT into A0, the initial concentration, into 1 minus e power, this value you write it. What is meant by e power minus K1 plus K2 plus K3 and T? This is nothing but the fraction remaining unreacted. That is 1 minus T is equal to what? The fraction reacted. Fraction reacted means that is the fraction is converted into product, that is given by this equation. For example, A giving 2B and 3C and 4D. Let us assume for B concentration of B at time T is given by Ni, that is 2 into, and what is the K value? Multiply what is the initial concentration, what is the total K. And using this formula, it's a lengthier one. It will not be given, I think so, in the CSR examination because it's a lengthy process. They won't ask this. However, you should remember this. Okay, but we are going to calculate what is the concentration of the products at infinity. What is the concentration of the product at infinity? That is, infinity means reaction is complete. T is equal to half. Reaction is complete means here products, no reactant is present. All of them are converted into product. Let it be K1 mode, K2 rate constant, K3. In such a calculation, we can work out the concentration of any species at infinity as Ni Ki, Ni Ki divided by N1 K1 plus N2 K2 plus N3 K3 and so on. If these are all 1, 1, 1, you will get K1, K2, K3. Okay, and Ki, this is one. This is the fraction of the concentration. If the initial concentration of A0 is given, this is the concentration obtained at infinity. You are obtaining the concentration at infinity. What is the concentration of B mode? C is the mode, ith mode of the concentration. How much C, how much D can be obtained. Now we will take a problem in this case. Take down the problem. It will be easier for you to calculate this. A parallel reaction of the type, first order parallel reaction of the type is given as 2C, 2 per minute, or B, sorry, C 4 minutes, and D 1.5D at 6 minutes per minute, K values. The initial concentration of A0 is equal to 2 mole. Initial concentration of A is equal to 2 mole. what is the final concentration, infinity concentration of B, C, and D. That is concentration of ith mode at infinity is given by NiKi. Because here we are going to calculate the product concentration, you should make use of the stoichiometry given. NiKi. And by N1 into K1 plus N2 into K2 plus N3 into K3. This is a fraction of the amount of time into the concentration of A naught. Because A naught is completely converted, this A is converted into this one. Now, you can calculate the concentration of B infinity. Last we have seen the B of concentration at time t. It's a lengthier one. No question would be asked in that I have told you. B infinity, here question may be asked the infinity time. No A is present. All of them are converted into product. In order to find out the concentration at B, you should make use of the stoichiometry in this. What is the total products? These are called the total products obtained by the fraction present. Ni, what is Ni? We are calculating for B, the first mode. What is the number of modes for these? 2 stoichiometry. Ki is 2 divided by and N1 into K1. And the initial concentration is also 2 by N1 into K1, 2 into 2 plus N2 into K2, 4 into 1 plus N2, N3 into K3, 6 into 1.9, 1.5 equal to 8 by 9, 30 and 70. 8 by 70. 8 by 70. And similarly, C at infinity is given by here Ni, Ki and this one. Ni1, Ki 4 into A2 by, this is a constant equal to 17. Therefore, 8 by 70. And next one, D infinity equal to Nki 1.5 into A naught 2 divided by the one is given by 12 into 1.6, 18 by 7. Therefore, their ratio is 18 by 7, 18 by 17 into 118 by 70. If you sum up these, it should be equal to the 2 moles. And this product and these products are found to be same. Whether it is found to be same, multiply these two, find out, yes, they are found to be same. Therefore, what would be their concentration versus time plot? And here, one is going on decreasing. This is due to water and variance. And one is from 0 to going on increasing. Another is going to increase. Here we are having 3 different products, but here in the situation we will get only 2 products concentration. Why? For which you should, which is having higher product, which is having lower product. I have already given to you, for which you have to find out Ni, Ki. For first one, N1 into K1 is equal to what? For second one, N2, K2 is equal to what? For the third one, N3 into K3 is equal to what? Multiply and tell me the answer for B mode. For B mode,
4, sir.
4. For the next one, N2, K2,
4, sir.
for D mode. K3 is equal to 6 and the stoichiometry is 1.5. It is 9. Which is the major product?
D, sir.
D. Therefore, which curve is representing the D? Upper curve or this lower increasing curve? Which one?
Upper.
D. This is the increase in the concentration of D with the time. And here the remaining two. They are all equally formed. Same their curves will be lying one over the another. You can't get the two different curves. Therefore, this curve is due to B as well as C. Do you understand this?
Yes, sir. Thank you, sir. Thank you, sir.
Okay. Next to the last type of problem here, we are going to this concentration of any product at any time that is given by concentration of the ith mode by concentration of the jth mode is equal to the stoichiometry of the ith mode into its Ki by stoichiometry of the jth mode and the Kj. The last problem we have discussed, what is the concentration of B by concentration of C at any time? That is given by, anybody tell me the answer, what would be the concentration at any time t? That is nothing but Ni by Ki by Nj by Kj. The B க்கு 1 I ன்னு வச்சிருக்கோம், C க்கு J ன்னு வச்சிருக்கோம். Now tell me Ni, what is Ni? 2 moles into Ki 2 moles divided by C. So stoichiometry is 1 into 4. 2 by 4 by 4 equal to that. Always B by C concentration is equivalent at any time t. Another we have obtained the curve 1 over the another, we get a single curve. Now, what would be the concentration of B by concentration of D? Can anybody tell the ratio of this B by D? Yes, it can be easily told. It can be told. 1 into 4 by 6 into this 4 by 9. Similarly, C by D or D by D, it may be asked at any time D by D or C by D. You are ready to give this one. Therefore, depending upon their N and K value, the concentration will be in this. If you understand this one, you work out this problem, the last sum for this one. For a first order parallel reaction, K1 and K2 are in the ratio, that is K1 bracket plus B and K2 C product in the ratio 4:9. If the sum of the concentration of B and C at any time, is 2 molar, sum of the concentration of B and C at any time is 2 molar, then what will be the concentration of B and C at time t? A 11 by 12 molar and 13 by 12 molar. B 3 by 4 molar and 5 by 4 molar. C 4 by 5 molar and 6 by 5 molar. B 8 by 13 molar, 18 by 13 molar. Here B plus C concentration is equal to 2 molar. The total concentration present is 2. And what would be the ratio in that 2 molar? What is the concentration of B? What is the concentration of C? The 2 molar. Here, the ratio of B, K1 is 4 and it is 9. Therefore, which concentration should be always higher? Which concentration? And here, one stoichiometry is not given. Therefore, taking it to be granted as 1. Which molar concentration should be higher and which molar concentration should be higher? Lower at any given. C should be always higher and D should be lower. Therefore, in the look at the answer, C concentration is given always larger. If any answer is given in the reverse manner, you can simply cut it off because it's a wrong answer. And the next one is B plus C added, you should get 2. Here add everything. If you are not getting that one, remove that answer. After this, sometimes by doing this, you will end up with only one answer that is the correct answer. Well, let us try our luck. Here always 4:9, it is always given lower than the BEC. Therefore, the luck is not working now. So sum of this, whether you get the 2 molar, in all cases it's found to be 2 molar, is not? Therefore, that luck is not also working now. Therefore, you have to go by the calculation. How to work out this calculation? 2 problems. So what is given? The ratio of B by C at any time is given by Ni K1 அப்படின்னு சொன்னேன் இல்லையா? Here it is given in this present in the ratio 4:9, that is 4 by 9. K1 is 4 and is 9. B by C is equal to 4 by 9. This one equation is given, but you have to find out individually B and individually C. 2 unknowns are there. Therefore, you are in need of one more equation. What is the equation given? B plus C is equal to D. Therefore, it is now very easy for you to give 4 by 9 into C. Here B is equal to 2 minus by C minus C at time T. T போட்டுக்கோங்க at T. Therefore, instead of PT, you should substitute as 2 minus CT equal to 4 by 9 CT. Now work out equal to 18. 18 is equal to 13 CT, or CT is equal to 18 by 13. Am I correct? Am I correct? Do you understand this?
Yes, sir.
But now I am going to do the same problem in a shortcut manner without using this one. How to work out this? What is the total ratio? 4:9. What is the total? 13. Of which, how much is present in KB? 4. The concentration should be 4 by 13. And what is the concentration of C? It should be 9 by 13. It is the in unit, in fractional unit, F5 we have given. Fractional means the in concentration present is equal to 1 molar. What it is given concentration is 2 molar. Just multiply by 2. 8 by 13, 18 by 13. The answer is here, right or wrong? Hello, understand this or not?
Yes, sir.
If you understand this, now work out this problem. The ratio of K1 and K2 is 3.4. The total concentration of B and C is equal to 0.4 molar. What is the concentration of B and T at time T? Immediately tell me. What would be their concentration ratio? B should be 3/7, C should be 4/7. If the total concentration is 1, this is a fraction. But 1 point,
2 by
1
7,
point, next one,
1.6 by 7.
7. Or you can, given in a simplified manner, or in a, what would be their ratio, right? This is the way you can be given this one. Okay? And shall we move to the last type of kinetics, consecutive reactions? And what do you mean by consecutive reaction? Now, we are seeing A giving B product irreversible, A giving product in the reversible manner. This is a equilibrium reaction. A giving B and C is called as the competitive reaction or the parallel reaction. Now we are going to see A giving the product B, but not in one step as in this, not in like this, not like this, but in a different manner. What is the manner? The reaction which proceeds, the reaction which proceeds from the reactant to final products through one or more steps, more stages called consecutive reactions or sequential reactions. Consecutive reactions or sequential reactions. You can come across such as sequential reactions. We have written for writing the mechanism of the complex reactions. In the complex reactions, they are taking place in more, two or more steps here. In that, the first step, the reactant giving some intermediate, we call it as the initiation step. You all know that one. The last steps, which is giving the intermediate to product, we call it as the termination step. And all other intermediate products are called the propagation step and so on. Here, the problems are calculating the BT or the intermediate concentrations, IT, and this one is a tedious. And I am going to give you, in summary, what are the equation and in which equations you are asked to work out the problems. That is sufficient to do exercise in that equations. Okay. First, we will consider the equation A giving B giving C. So K1, K2. Here we once again assume A is a first order, B is a first order, C is a, C is first order. A is first order, B is a first order. This is the simplest to derive the relationship. Sometimes A may be a first order, B is a zero order. The derivation is different. Or A is a second order and B is a first order kinetics. It is also different. Here, for our simplicity, we assume A is a first order and B is also undergoing first order kinetics. And here, the once again, the rate law equation is given as AT is equal to A0 e power minus K1 minus K1t. Similarly, you can calculate the concentration of B at the time t, the calculation of the product at the time t, but these equations are very lengthy. Therefore, we are not going to consider that equation. Instead, we apply limitations for this. Case 1, in which the K1 is found to be very, very fast compared to K2. That is a rate of formation, that is A to B conversion is very fast, whereas B to C conversion is less or slow. Therefore, what happened to, if you see the concentration versus the time, where the concentration of A is going on decreasing, okay, as usual. But what about the concentration of B and concentration of C? Here the concentration of, in the case, K1 is very, very higher than K2. Therefore, the concentration of B is going to be accumulated, whereas the conversion of B to C is slow. Therefore, the B is going to increase, reaches a maximum, and then coming to a minimum. Therefore, this is called, we call it as a B max. But all other situation, we won't get the maximum. Here we are getting the maximum. And what about the concentration of C? The concentration of C is slowly, it is going on increasing. Therefore, for this case, B is attaining the maximum, and this is B and this is C. Here, two derivations are important. What is the two derivation? The derivations we are not going to give. What is the maximum concentration of B? That is given by A naught into K2, that is lower speed by the higher speed, into K2, the lower speed, by K1 minus K2. This is the equation. But no problem is so far asked. However, this time it may be asked. Next to T max, the time taken for the concentration to reach the maximum. What is this? This is the answer. What is the time taken for this one? For which the answer is T max is equal to 2.3 into log K1 by K2, higher by this, divided by K1 minus K2. This is the equation. We are going to use these two equations for the purpose, this one. First, we take down the one problem in this distribution of the concentration. Then we will go for the next two one. Take down, it is asked in the year 2006. A reaction proceeds. The reaction proceeds through the formation of intermediate. Through the formation of intermediate. B. In a unimolecular reactions. In a unimolecular reaction. Take down the unimolecular reaction. A giving B, giving C. This is Ka, this is Kb. The integrated rate law for this reaction is option A. A is equal to, that is concentration at time is equal to concentration of A at 0 time as e power minus Ka T. B. Concentration at time T is equal to concentration at e power minus Ka-T minus e power minus Kbt. C. Concentration of A at time T is equal to concentration of A at time 0 by 2 into 1 plus Ka into e power minus Kbt minus Kb into e power minus Kat by Ka minus Kb. D, concentration of A at time t is equal to concentration of A at 0 time into 1 plus E minus Kat minus E power minus Kbt. This is the question first asked. What is your answer? I have already given the rate law equation. The is equal to what is the equation I have given? What is the answer?
AT is equal to A for paper.
E power. The first answer, A answer is not. This is the answer. These are all the, not at all the answer for it. Okay, continue. If Ka is greater than, very, very greater than Kb, then the concentration versus time plot, then the concentration versus the time plot for the above reaction is, option A, option B, option C, option D, which is the correct one. When K2, Ka is very, very greater than AB, what happened? We have seen in our limiting case 1.
Option B.
Option
B.
B is the correct option. Here also a maxima is there in the C, but the decrease in the concentration of A is not according to exponential decrease. Therefore, it is not given. And all other cases, no maxima for B is given. Therefore, A, B is a, this is asked in the year 2006. Now we take down another problem. If the initial concentration of A is 2 molar per liter, 2 molar per liter, mole per liter, sorry, 2 mole per liter, and K1 and K2 are 0.3 per minute and 0.5 per minute respectively, comma, at what time the concentration of B in the following reaction will be maximum. The following reaction will be maximum. A giving B giving C, K1, K2. And also calculate B max. First option, 4 minutes, B 6 minutes, C 2 minutes, D 8 minutes, which is the correct answer. First to do the problem, then we will go for the B maximum problem. What is the T max? Write down the T max problem. T max is given by the equation Tell me that equation T max is equal to 2.3 into log of
0.6
K
by 0.3.
divided by K1 minus K2. This K2 is, I have given the wrong data. Here K1 should be greater than K2, but here the value is 0.3, 0.15. Put it as 0.15. K1 is greater than K2. Therefore, here the wrong data 0.5, 0.15. Now substitute and find out the answer for the T max. 2.3 into log of K1 is equal to 0.3 by K2 is equal to 0.15. That is equal to log 2. Log 2 is equal to 0.3. Is now by K1 minus K2 0.15 equal to log 2 is equal to 2.3 into 0.3 by 0.15 equal to 0.69 by 0.5. Nearly how much? Answer is? Answer
12.6.
is that you can convert into 0.7, 0.4 minutes is not a point.
சார் 0.15 0.3 கேன்சல் பண்ணிடலாம் சார் அங்கேயே. ஸோ
சரி.
2.3 into 2 வந்துடும் சார்.
ரைட்டு, எப்படினாலும் பண்ணுங்க. Not 5. 4.6. ஓகே, 4.6 இங்கே வந்து நம்ம அப்ராக்சிமேட்லின்னு வார்த்தை வச்சு எடுத்துக்கோங்க. 4 minutes 4 approximately அப்படின்னு போட்டுக்கோங்க. Okay, then calculate the B max at the time 4 minutes. What would be the B max? Option for the B max, it is 0.5 mole per liter. B option 0.75 mole per liter. C option 1 mole per liter. D option 1.25 mole per liter. What is the equation to be used? B max is equal to
K0
K0 into K2 by K1 into K2 divided by K1 minus K2. K0 is given as 2 mole, K2 as 0.15 by K2 as 3.3 into 0.15 divided by K1 0.3 minus 0.15. Therefore, equal to 2 into this will be equal to power what?
1.
1. What is the answer for this?
1.
Molar per liter. Yeah. And this type of problem so far not asked in CSIR. And we will work out for the case 2. This is for the case 1. We will work out for the case 2. What is the working out for the case 2? It is very easy. Now, which would be put as higher, very, very higher than next one? The first case we have put K1 is very, very higher than this one. Now we have to put which is as the very, very higher for case 2. K2 is very, very higher than K1. in the consecutive reaction A plus B giving C. That is, the K1 value is less, K2 value is very higher. What happened in the situation? A to B is taking place slowly, whereas B to C is taking place very fast. Please imagine the situation. A, formation of B is very slowly taking place, but the conversion of B to C is very fast. Therefore, what about the concentration of B at a given time?
Almost
Or
zero.
almost zero. Such species B is called transient species. The concentration is very, very, very small because as and when it is formed, it will be converted into the C. It is called the transient species. Concentration is very, very slow. For such cases, steady state hypothesis is applied. Steady state for which one? For transient species. If a transient species form and what is the condition at which transient species should be formed? The rate of formation of that particular intermediate is slow compared to its rate of consumption. Steady state. Under this condition, if you plot the concentration versus the time, as usual, the decrease in the concentration of the reactant is exothermic decrease. And here the concentration of C is very fast, but the concentration of B is initially starting small and it would be reaching a steady state. And the concentration is initially zero, but it is going on increasing. Therefore, this decrease is A. The concentration is very small and is remaining almost constant is there. A steady state approximation species, that is transient species B, and this is the C. This is the distribution of the concentration in this one. And in such cases, we can assume a steady state hypothesis. Under the steady state hypothesis, the concentration of C at a time t is given by initial concentration A into e power K1 into E. Your rate is now depending upon the K1, if it is the slowest step, therefore K1 into T. For the former case, I have forgotten. For the case 1, I have forgotten to give the concentration of T, product at the time T. That is also A0 into 1 minus e power minus, and there K2 is very, very small. Therefore, that is the rate determining, and K2 into T. Now, take here, look into these two equations. Here K2, which is very low, that is the percent here, the exponential. And we will work out some one or two problems in this, and we will close this chapter. Take down this. Examine. This is asked in the year 2014. Asked in the year 2014. Examine the following first order consecutive reactions. Consecutive reactions. The rate constants, bracket in within bracket in per second unit for each step is given above the arrow mark, given above the arrow mark. Steady state approximation can be applied. Steady state approximation can be applied to options steady state approximations can be applied. So now what is the correct option?
D.
D is the correct option. What is the, when you apply the steady state, the K1, the first rate of formation is slow, the second is fast, then the intermediate species is said to be transient species. For such a transient species, we are applying steady state. Here, 10 power 5, but the consumption rate is 10 power 8. Here, the consumption rate is slow. Inge enna nadakum? What happened for this reaction? Here 100 times is slower. Therefore, what may be obtained here? Accumulation of Q, or a Q maximum would be obtained here. Here, what happened? Equivalent. Therefore, the rate of formation is equal to rate of the consumption. Here, accumulation as well as complete transition is going on there. Here also there is a transient species there. Therefore, which is the correct answer? A and B. And now take down the another problem. For the chemical reaction, A giving B K1, A giving C K2, B giving C K3, and C giving B K4. The rate constants K1 and K2 are at least 1,000 times slower than either K3 or K4. During the course of the above reactions, the ratio of the products, B and C will be, take down the option, which is the correct answer here. If you understand this one, what is the concept you should understand this? Here K1, K2 are very slow. And if you first draw the diagram for this is A giving B, A giving C. It is a parallel reaction. It's a K1 and K2. The parallel reaction B giving C is a K3 and C giving back the B K4. A parallel reaction and the products are in equilibrium with this one. Here what is asked? What is the concentration of B and C at time T? Here the concentration of B formation is due to the K1. What is the concentration of B formation? It is equal to K1 into A. K1 is lower, K2 is also lower, 1000 times lower this one. These two are very fast. And which is the rate determining step, K1 and K2 are the rate determining step. We won't consider in the rate law equation and the K3 and K4. Therefore, whatever may be the K3 and K4 you derive, you won't consider in this one. You will consider only the K1 because rate determining step. 1000 times is slower. Therefore, the concentration of B is depending upon K1 into concentration of A, not on the concentration of C, or what is the rate at which B is going to A and B going to C and C going back to B. It depends only upon the concentration of A. Similarly, so is the case with the concentration of C is depending upon the rate constant of A into the concentration of the A. Not on the K3 and K4 value because they are very fast. And if you cancel this, you will end up with this the answer. This is not so far asked, but I think it may be asked. And take down the final question as an exercise. I don't know how to solve this problem. If anybody coming across solving this problem, please, before which I will give one more problem which is given in the year 2003. In a consecutive first order reaction, A giving B, K1, B giving C, K2, within bracket, where K1 and K2 are respective rate constants. Comma, species B has transient existence. Species B has a transient existence. Therefore, option A, K1 is equal to K2. Option B, K1 is equal to 2K2. Option C, K1 is very, very greater than K2. Option D, K2 is very, very greater than K1. Which is the correct answer? Tell me.
Option D. Option D.
Option D is there. Suppose this is to be an answer. Question should be modified as. And this should be the answer. Question should be modified as what? The species B, என்ன நடக்கும்? Attains a maximum concentration. அப்படிங்கிற வார்த்தை வந்து this is the one, but here it is found to be a transient existence. Okay, take down the last problem to be done in your home, but I find no way to calculate this one. If anybody find the shortcut to calculate this one, this problem is asked in the year 2004 for the reaction of the type. B giving Q, K1 and R, K2, given that P, concentration of P is equal to 1 molar, K1 is equal to 1 into 10 power minus 3 per second. K2 is equal to 1 into 10 power minus 4 per second. The time at which the concentrations of Q and R, ARER, answer எழுதிக்கோங்க 0.0966 molar and 0.0355 molar respectively is option 500 seconds. B option, 750 seconds. C option, 1000 seconds. And D option, 1500 seconds. How to work out with shortcut? I don't know if anybody work it out, please post it. And with this, I finish the possible problems to be asked in this ASR examination. The next type of topics we have left is the kinetics of photochemistry or photochemical reactions. Kinetics of photochemical reaction. It is not dealt with. The kinetics of polymerization reaction. Kinetics of polymerization. Then next is the theories of rate or rate constant, theories of rate, another collision theory, the Lindemann hypothesis, and the activated complex theory, etc. The last one is catalysis. Catalysis, homogeneous catalysis and heterogeneous catalysis. In the homogeneous, especially is the enzyme catalysis, Michaelis, Menten, equilibrium constant. அப்படின்னு சொல்லிங்களே, enzyme is a constant, enzyme catalysis. Okay, thank you students. See you.